Daniel Bernoulli, a Swiss scientist who was born in 1700 and who died in 1782, discovered certain properties relating to fluids in motion. He expressed these properties in the mathematical statement that the total energy in a moving fluid or gas is made up of three forms of energy: the energy due to its height or position, the potential energy, the energy due to its pressure, and the energy due to its movement, the kinetic energy, and that in a streamlined flow of an ideal fluid, the sum of all of these is constant. If we just consider airflow as opposed to any other fluid or gas flow, the potential energy in that airflow can be assumed to be constant. Thus, we can modify the previous statement for all practical aerodynamic purposes by saying that the kinetic energy plus the pressure energy of a smooth flow of air is always constant. Thus, if the kinetic energy is increased, the pressure energy will drop in proportion so as to keep the total energy constant. A practical application of Bernoulli's theorem with which the pilot should be familiar is the Venturi tube, sometimes called a convergent-divergent duct, an example of which is shown here. The Venturi tube has an inlet which narrows to a throat, and an outlet section, relatively longer, which increases in diameter towards the rear. For a flow of air to remain streamlined, the mass flow passing a particular point in a set period of time must remain constant. So, if a Venturi tube is positioned in such an airstream, then, for the air to remain streamlined, the mass flow through the Venturi must remain constant. The mass flow is dependent on the area times the density times the velocity, and is a constant. This statement is known as the continuity equation. Assuming that the density remains constant, for the mass flow to remain constant and still pass through the reduced cross-section of the throat of the Venturi, the speed of flow through the throat must be increased. Bernoulli's theorem states that this will bring about an accompanying pressure and temperature drop. The use of Venturi tubes has many applications in aircraft systems. One such example is the Venturi which is used to create the pressure drop at the throat of the carburetor, as shown here. Gases behave differently from the other two commonly studied states of matter, solids and liquids, so we have different methods for treating and understanding how gases behave under certain conditions. Gases, unlike solids and liquids, have neither fixed volume nor shape. They are moulded entirely by the container in which they are held. There are three variables by which we can measure gases: volume, pressure, and temperature. We'll discuss two of the so-called gas laws which are most pertinent to the operation of the internal combustion engine: Boyle's law and Charles' law. Robert Boyle was born in 1627 in Ireland. He made important contributions to physics and chemistry, but best known for the law which was named after him concerning an ideal gas. Boyle's law states that, in a gas which is held at a constant temperature, the volume of that gas is inversely proportional to its pressure, or pressure times the volume equals a constant. This holds true where P is the absolute pressure of the gas, and V is the volume occupied when the pressure is P. This is a reproduction of an experiment carried out by Boyle. He had a calibrated syringe filled with air and deduced its volume. While taking care to retain the temperature of the air inside the syringe constant, he increased the pressure and decreased the volume inside it by placing weights on its plunger, taking readings as he did so. You can see that by multiplying the volume by the pressure, the answer remains a constant. Hence, the product of the absolute pressure and volume of a given quantity of gas is constant as long as the temperature of the gas does not change. Try moving the plunger up and down yourself to simulate changing the weight on it, and note that the result of P times V always remains a constant. Because of the interest in hot air balloons in the early 1800s in France, Jacques Charles and Joseph-Louis Gay-Lussac made detailed measurements on how the volume of a gas was affected by its temperature. Just as Robert Boyle made efforts to keep all the properties of the gas constant except for the pressure and the volume, so Jacques Charles took care to keep all properties of the gas constant except for its temperature and volume. Charles' law, or Gay-Lussac's law, states that if any gas is held at a constant pressure, its volume is directly proportional to the absolute temperature, or, if stated as a formula, the volume divided by the temperature is a constant. Just as we did to demonstrate Boyle's law, we'll replicate an experiment similar to one carried out by Jacques Charles. If we partially fill a calibrated syringe with air and place it in a container of water, then by increasing or decreasing the temperature of the water, and thus increasing or decreasing the temperature of the air inside the syringe, while taking readings of the volume and temperature, and then dividing volume by temperature, in degrees Kelvin, we see that the answer is a constant. Remember that, in theory, the pressure inside the syringe remains constant also. Try changing the temperature of the water for yourself, and notice that the result of the volume divided by the temperature remains a constant. Although both Boyle's law and Charles' law work in theory, we are unable, with existing technology, to make them work in practice. For instance, it's impossible as yet to increase the pressure of a gas without increasing its temperature, because of the adiabatic heating which inevitably occurs. Remember the example which is consistently quoted of how a bicycle pump always heats up when air is pumped into a tire. By using Boyle's and Charles' law together, we get a practical method of determining what is happening to the gases inside the internal combustion engine, where temperatures, pressure, and volume are all changing constantly. With the scientists' usual lack of imagination, they've named the integrated Boyle's and Charles' laws the combined gas law. The combined gas law represents the relationship between volume, pressure, and temperature. This relationship indicates that for any two given conditions within the engine, which we may label condition 1 and condition 2, pressure times volume divided by the temperature is a constant. This is commonly shown as P1 times V1 over T1 equals P2 times V2 over T2. The changes in pressure, volume, and temperature within the engine cylinder as the piston moves between the top and the bottom of its stroke are illustrated in the following animation of a purely theoretical engine. In a practical engine, both the valve and ignition timing has to be radically changed if the engine is to have any chance of running at all. On the induction stroke, the piston moves down, increasing the volume available for the incoming mixture, and the pressure inside the cylinder thus reduces. Use the repeat button to show the process again. On the compression stroke, the cylinder volume is reduced. Because both the inlet and exhaust valves are closed as the piston rises, the pressure inside the cylinder increases, as does the temperature. Use the repeat button to show the process again. In this theoretical engine, combustion is assumed to occur instantaneously at top dead center. Because of this, the engine is said to be a constant volume engine. However, as we shall learn later, in the practical engine, combustion actually occurs relatively slowly. The power stroke in the theoretical Otto cycle starts with the mixture being ignited and simultaneously burning with the piston at top dead center. The resulting initial rapid rise in temperature expands the gases, increasing the pressure in the cylinder, driving the piston down. Subsequently, as combustion ceases, the volume of the cylinder increases, the pressure will fall, and with it the temperature. Use the repeat button to show the process again. On the exhaust stroke, momentum keeps the piston moving. As it rises, the volume inside the cylinder decreases, and even with the exhaust valve fully open, the pressure will rise slightly as the piston ascends to expel the gases to atmosphere. This will cause the gas temperature to increase slightly. Use the repeat button to show the process again. This is the end of the first sortie into the mysteries of the internal combustion engine. In the next lesson, we'll investigate a few more definitions and then delve a little more deeply into the way the piston engine is built.